Hello everyone, my name is Alejandro Lucero and I'm going to talk about a new technology, CXL, and how I think it can help with SmartNICs doing obvious hardware offload. I need to start with a disclaimer because I work for AMD, but I'm not representing AMD in this talk, so this is just me eager to discuss a potential use case of CXL. This is the agenda. Um, I think I have just 25 minutes, so probably I will not reach the context and multi-tenant OpenFlow point, but all of this is written down in a paper that I will give as a reference. So let's start. CXL is a new technology starting to get a lot of attention. It helps with sharing data between hot CPUs and high-performance devices like GPUs. It is going to have an impact on other areas as well, and networking is not going to be the exception. Nowadays, everyone is talking about, or a lot of people in the industry is talking about memory expanders with CXL. But it's a really hot theme to discuss. Anyway, although this data sharing can be done with PCIe devices, with CXL the way of doing this is more suitable for this data sharing. It comes with theoretically lower latency and the full coherency handled by the protocol. One could easily think CXL can help with the data path, that is for sending or receiving packets, but this talk is about the control path, where CXL could have a great impact on improving latencies, likely having also simpler designs in the devices, and with the proper support avoiding a lot of code in the kernel. Why am I talking about this today? Well, I have worked in two different SmartNIC projects, two different companies, and both supporting OVSDC, hardware offload. Since hardware offload was initially implemented within the kernel, it has not changed too much. And the question is, does it need to? Well, my point is, for properly supporting massive virtualization, that is servers with dozens of VMs, the kernel TC is not the right solution. I will talk about the main problems with TC, and let me say at this point that the key aspect, or one of the key aspects, was ignored or maybe not considered so important, and that is the rate of change, how the obvious rules or contract states are handled by current approach. So I state here that due to a far from optimal software data path execution, along with the dismissal of the importance of control path updates, far more CPU cycles in the host are used, what is not just a problem leading to higher latencies when handling packets, but it also puts more pressure back in the software data path itself. After studying the problem from different perspectives, obvious kernel DC, hardware offload support inside the kernel, the drivers, the hardware, I realized the current approach cannot work properly. Improvements can be done, but it will require a good effort and it will likely not be enough due to the problem itself. So I really think we have an opportunity with CXL for solving the problems, making the control path updates easier, faster, and saving resources. The more I think about this, the more I'm convinced, and hopefully I will convince you, or at least make you think about it. Let me now specify the type of SmartNIC I'm referring to. Although this being an obvious conference, this is going to be easy. The focus is on SmartNICs helping to accelerate networking for virtual machines. So a VM talks straight to the hardware through virtual function. Therefore, we have things like SROV, IOMAU, maybe VDPA. Those SmartNICs will handle packets through match and action rules, as OVS does, implying a packet from the wire can be sent straight to the specific VM without any host intervention, and vice versa. I'm assuming here you are all familiar with the dual hardware-software data path. SmartNICs implement this match and action with hardware comms, which is really good as the matching is done in parallel and at speeds not possible with software solutions. The problem being those comms are really demanding in terms of power and space inside the chip. So the bigger comms are in the order of the low thousands entries. And a SmartNIC can have several comms, creating a pipeline helping with processing packets based on packet or flow states. But the main problem is, at least for the case of massive virtualization, those comms are far from what is needed in terms of number of rules and flows to work with. The way SmartNICs solve this problem is with DRAM inside the device, where rules and flows can be installed in the millions. This picture, that is a simplified view of this type of SmartNIC, whatever happens inside the gray box in the middle, where the supposedly comms pipeline occur, is up to each vendor and is not going to be discussed here. The important bit is that pathway between the gray box and the DRAM, and with a design like this, the hardware will handle the situation when a packet is not matching any rule in the comms. So with the RAM being there, it will be accessed then for using any rule of flow state installed there. Again, how this is done is not important for the sake of what I want to present here, and all that is the secret sauce of the vendors. What I'm really interested in is in the control path, that is how those comms and DRAMs entries are populated from the host. So it's time to talk about how this type of SmartNIC is being used along with the current kernel and OVS, along with the Linux kernel and OVS. First of all, I don't think I have to convince you about the way OVS works and its benefits. The only thing I want to mention is the main point of, or my main statement about the rate of change being a problem, what I mentioned earlier, and which, if true, is a serious problem for the reactive mode usually required for this model. Although there are other solutions relying on the same model of closely related software-hardware data paths, I'm going to talk about the obvious TC solution, so packets handled by the kernel traffic controller in the ingress and using TC flower. The so-called slow path, which implies an obvious user space component deciding what to do with a packet that has not a rule to handle. It is not relevant in this discussion by itself, although it is what happens when that decision is taken and a new rule will be installed in the kernel DC, and if there is a SmartNIC supporting obvious DC, the offload of that rule to the hardware. Once the rule is installed in the hardware, the packet and subsequent ones matching same rule will be processed by the hardware, saving CPU cycles in the host. But it is necessary to say that it is not always as fast as desired, with the latencies being not deterministic and implying a number of subsequent packets will still go through the software data path in the host. Moreover, if conntrack is used as part of the matching in the offloaded rule, the packets needs to still go to the host anyway until the flow state can be offloaded once handled by the conntrack component. It is not necessary to say that rate of change about this type of contract states per flow is far more demanding than rule changes. So why is the kernel TC being used nowadays? I'm not going to talk about the historic decision. I think it was a mistake because the assumptions made, as I said at the beginning of the talk. I have this paper where I wrote all this CXL idea where I describe the situation. The important question here is if does it work? Kernel TC, does it work for what we need? Well, the answer is yes, the functionality is there. But does it work with the required performance for the case of massive virtualization, or more specifically for OVS? So apart from the jokes, it is a fact that some assumptions have changed since the times where TC was designed and implemented. The performance gap between the CPU and the current network cards is bigger. So handling packets with CPU execution is more problematic now. And because, as I have described before, the software data path performance does matter, and because the hardware offload mechanisms does matter, I dare to say TC is not the right solution. This doesn't mean TC can not be useful for other things. So this is not an attack on TC at all. It is simply the ground functionality for a system with dozens of VMs and where any latency when handling packets is important. Maybe you are aware of those problems. What I'm referring to about TC problems. Maybe you are not. In any case, I describe in detail all this in the paper. So I'm going to assume we agree on this for the sake of the following slides that the TC is a problem. Interestingly, there is some movement in the Linux kernel networking about using a flexible data path, fully programmable data path based on P4 or ABPF. This could theoretically solve some of those problems I have mentioned. Let me say that any solution which could really overcome the known limitations is welcome. And for the sake of this presentation, regardless of how that could finally be implemented, what I care about is how the data of the control path will be represented. It will be represented. So those structs and algorithms involved. Because one reason behind the P4 proposal is the hardware and the software will be equivalent in functionality and coming from the same source. Let me ask then, could both use the very same data? This is a bit of a spoiler of the CXL solution I'm going to present. But before that, I want to talk briefly about other problems with OVS-TC, in this case the hardware offload. So when a TC role is updated and there is hardware supporting it, supporting this OVS-TC hardware offload, this happens synchronously to that rule update through the specific driver. An initial problem is TC QDs cannot be updated in parallel. Also, in terms of processing the offload, the driver needs to check if the hardware supports the matching and action of that rule. Then it needs to translate all the TC semantics to what the hardware understands, and then the rule is sent to the hardware. How that sending is done is important. There are several possibilities. One is using the same device data path, or there may be using a special channel. In any case, it requires something in the device dealing with the new rule to be used, and then the hardware will likely add the rule update and send some identifier back for the driver being able to refer to that rule in the future. actually the driver keeps a lot of information about the rule apart from what the kernel TC keeps itself. I will talk about that again in the next slide. And the question is, once is in the hardware, once it has been sent to the hardware, how does that rule end up inside the CAMs or inside the DRAM? How long is the latency until it is really used by the switching logic? Is it deterministic, or could it be latency peaks far above than the mean? With conntrack is quite similar, but it starts asynchronously and kernel coworkers are used. For a high rate of change, what we should expect if conntrack is used, this is a really heavy load for the system. Moreover, if the hardware offload for conntrack is not optimized as it is the case. An important question is when the kernel kworkers will start processing those items, and maybe who will be charged for all those CPU cycles. Once the coworkers are are starting the hardware offload, the steps to follow are equivalent to the rules commented before, and the same problems about when that flow state can be really used by the switching logic. Trying to make all this easier to understand with this picture, the data ends up being duplicated in the host and inside the device in both DRAMs, and this is even worse if we count the data kept by the related driver during the hardware offload. As I have mentioned, the offload requires a good number of CPU cycles by the driver, and not always it's not possible nowadays to charge on the VM requiring the work, but it's another story. Those green lines there refer to how the CAMs and DRAMs are populated. It depends on the hardware design. In any case, it requires the hardware dealing with it specifically. And my point is, for this kind of SmartNIC design, will not all those rules and flows end up in device DRAM? Some could argue it will be better to write the CAMs, but really? Always? And what is the DRAM for then? So, as a summary, a part of the problem with the software data path execution through TC, the hardware offload is making things really bad. Some of this can be overcome with user space solution like obvious DPDK, where the software data path has been designed with optimization as the main goal. But the offload, the hardware offload, suffers similar problems due to the way SmartNICs handle the control path. So it's time to bring CXL into the picture. What about a control path where updates are just a matter of writing to memory, implying no driver intervention for offloads? Those memory addresses being backed by CXL memory inside the SmartNIC. This requires that the offload, the control data to be written in that memory, not having any specific of vendor, so it requires some standardization there. Maybe that specific format is required, but the idea is that it should be the hardware dealing with these translations when the device, the data from the device DRAM is given to was used inside the device CAMs. In any case, the host will not use CPU cycles for the translations, and therefore it will be a cost on the vendor. So with CXL handling coherency, the host CPUs can access the device DRAM for the software data path. Therefore, the data needs to be only in one physical place. The data path, the software data path code is in the host DRAM, but the software data path control data is in the device DRAM. So it only requires to be written once to the device DRAM and can be used by both the device and the host. Arguably, the software data path execution will be slower, but the CXL memory access latency can be theoretically is equivalent to accessing memory in a remote NUMA memory node. So trying to visualize the impact CXL could have here, note that the gray boxes imply same physical memory inside the device, that is seen by the host. So writing just once, all the rules and flows updates will always go to the device DRAM, and the hardware will focus on how the CAMs are populated, based probably in any proprietary algorithm. The host DRAM can also store match and action rules and contract flows as always, because it's an extension of what the hardware can do and extending the hardware limitations. So probably the most controversial point is the required standardization for the hardware data path. For the hardware control data. It can be argued this can not be imposed on vendors, that how they do things is where the difference matters, but this is only about how the data is represented in the device DRAM. Any special formats will be used when that rule or flow goes to the CAMs from the device DRAM. There are several good reasons for this. As I mentioned before, the cost of these relations not being on the host CPU cycles, so being on the vendor design. Also, because you can have solutions where CAMs are not there at all. In fact, there are some switches being implemented nowadays without CAMs and all based on large DRAM inside the switch. And finally, if that fully programmable P4 or eBPF-based software data path ends up being a reality, what is written to this device DRAM is up to that P4 program or eBPF program, because it's going to be completely linked to what the hardware does. Therefore, it doesn't require any standardization at all. So about the host using the data from the device DRAM, this is possible with CXL. It's not about the coherency, because there is no really a coherency needed here, because the host will update the rules in the device DRAM, and both the host and the device will see those rules, and the device is not going to modify those rules. So the coherency is not really needed. But the CXL protocol is more suitable for the low latency and better data movement required for the host software data path execution accessing that data. If this ends up being a reality and someone implements a solution based on this approach, I think probably the initial solution will be using cohasing for accessing the DRAM data. But probably if that occurs, I envision researchers proposing new ideas in the future. So I have just 1 minute, so I think I'm going to stop here. There are other two things that I wanted to mention briefly. The way the hardware counters are being updated in the host for the SmartNICs. I think it could be better done with CXL, with the orthogonality that CXL brings in. Hardware counters for SmartNICs are really demanding, and instead of sending the data regardless of someone really requiring it or not. It could be exactly that the case, that only when someone requires the data, those hardware context data, the context are updated in the host. And that's it, because the other thing is the OpenFlow multi-tenancy. That is quite challenging. I'm aware of that. Again, I refer to that paper for those interested in this idea. Really challenging. So, okay, I think it's now time for questions and answers. Thank you very much.